Hello and welcome to the module 4.5. In this, we will briefly learn about the concepts of correlation and causation. So, correlation is, in very simple term, why it is important for us to learn. Always, when two things are correlated, that does not represent the cause effect. What does that mean? If two things, A and B, are moving together, if A is increasing, then B is also increasing. That does not mean that this is a cause effect, that B is increasing because A is increasing. So we need to be very, very careful when we try to find out the association between two variables. We need to identify whether this is correlation. This is not always the causation. This might not be the cause effect. For instance, if you are just reading, okay, in a particular geographical location, if age is increasing, then the amount of money people are earning is also increasing. If you are getting this kind of correlation, this might not be the cause. Like the age increasing, the age might not be the cause of directly earning of the money. So we will discuss these things in very, very detail. This is a very important concept in the statistical analysis, and you need to be very, very careful while reporting these kind of results. So we'll go to the correlation versus causation. In this, ultimately, we are trying to distinguish the correlations from the causations, and we are trying to identify whether when two things are moving together, whether those are actually having the direct effect between A or A to B, or those are just the associations that we are seeing, not the direct relationship. We need to identify the confounding variables, we need to understand the Simpson paradox, and we need to study the strategy for the causal interference. You are seeing this kind of plot in any association study, any correlation study. You see these kind of scatter plot. When variable x is increasing, variable y is also increasing or decreasing, and that's how you measure the total correlation. In this, our learning objective is how to interpret the correlation coefficients. Then we'll recognize the confounding variables and other kind of variables. Then we will discuss about the Simpson paradox, and then we'll discuss the strategy, selecting the right strategy to infer the causality. Now, when you are inferring the correlations, when you are inferring the relations correlations, it's important to identify or adapt the right set of strategies to infer the causality that you might make, causality you might make during making those inferences. So for the first thing for you to know here is the correlation coefficient, R value. Whenever you will see a great scatter plot, when you will see people are trying to identify the association between two variables by doing the bivariate analysis, they will always report R value, R square value. What does that mean? This value varies from -1 to point +1. Stronger, the closer to the one, the stronger is the association, stronger the correlation. If it is positive, then a strong positive association. If it is negative, strong negative association. But these values are very sensitive to the outlier. When you will make a plot, x-axis is moving with the y-axis. If there is one or two outliers at the corner which is very high by value, those can drag the R square value towards the +1, towards the one value. So these are sensitive. So that's why we say correlation are not equal to the causation all the time. So we need to carefully monitor the cause effect. We need to understand the confounding variables. Confounding variable can be any third factor related to both exposure and the outcome variables. It can be associated with both, and it affect the outcome variables in terms of the exposure. So you need to identify those confounding variable. And when you are doing this association analysis, when you are doing this correlation analysis, you need to either remove the confounding variable, or you need to treat the confounding variable in such a way so that their effect is minimized, and we'll see how to do that. Can create the spurious association. Confounding variables sometimes can create the spurious association which might not be true, that disappear when controlling for the confounder. There is another confounding factor which is affecting the effect of A on B. When you will remove that confounding factor, you will not see a direct association. So treating those confounding factors, identifying and treating, is very, very important. You need to visualize the causal diagram, co-founders, exposure, and outcome. Is there any effect of co-founder by the exposure to the outcome? If it is, remove the co-founder, check the effect on the exposure of the exposure to the directly outcome. Example, you see age affecting both coffee consumption and heart disease. Socioeconomic status affecting both education and heart outcomes. So now you need to see what is the, if you are looking for the coffee consumption and the heart disease, if you want to see the association, if people who are consuming more coffee will have a higher heart disease, you need to consider the age factor here. Age can be super confounding factor here. Like You might see some of the heart disease, because in the individuals who are higher age, people who are, you will not see heart disease who are the lower age. So age can be a great you need to remove the age factor from here, and then you need to see the effect of coffee on the heart disease. So those kind of confounding factors are very very important to identify and to remove before reporting your actual results. Now the Simpson paradox, which is also very very important to understand. Same data, different conclusions. For instance, you are getting these data sets here, which is treatment, success, and rate. So in control, there are out of 13 success. Okay. And so the rate is 62%. If the success is 4 of 7, the rate is 57%. Treatment is better for men. This is your one conclusion. When you're taking for the Boomen, the success is control 12 out of 27, 2 out of 5 means the success rate for control is 44% and 40% in the Boomen. So success treatment is better for men here, treatment is better for women here if you are analyzing both data separately. But what if you are combining these data sets together, women and men all together? What will be the success? 8 and 12, 20 out of 40. So the success will be overall 50%. Here 4 and 2, 6 divided by 12, so treatment will be 50%. So treatment actually shows no effect overall if you will combine both male and female. So you need to understand how you are analyzing the data. You are analyzing the data for removing those kind of factors, considering all the factors separately, or you are using the data sets together. So it is very very important to understand the Simpson paradox. This is all about it. Like trends reverse when data is aggregated. So weighted average across the strata can mask the true effect within the groups. In this example we can clearly see this, and this is the Simpson paradox. When you combine, you might see the actual result that you stratify, or that you like, that is hidden when you are considering those variables separately or differently. So while making the statistical calculations, while making those kind of reports, you need to report the data. Either you are doing the calculation all in the separate categories, like in the men, you need to report it like this: the success rate in men is this, which is statistical significant. Success rate in women is this, which is showing the treatment is better for women's, or treatment outcome is there or not, or the success rate you are comparing in all together, not considering into the different group, not stratifying them. Those things need to be reported. And vice versa, if you'll report the results in any such way without combining the results, it might be not reflecting the true picture. So you need to consider that information also. Avoiding the Simpson pitfall, if you will avoid these kind of informations from resulting this statistical analysis, so it affect the design strategies like balance group by the key variables like gender, age, etc. It can affect the randomized treatment assignments. It can stratify the sampling by potential confounders, and you can use the match pair by or blocking experiments for doing that. Analysis strategy for this can be analyzed with the homogeneous subgroups. You can use the statistical adjustments, like you can do regression or economa type of analysis. Report both pooled and stratified results. That is very very important. If you are not correcting for the subgroups, if you are not doing the statistical adjustments, then report both. Like combined effect is this, and the individual group wise effect is this. Visualize data across different groups. That is a very good standard statistical practice. Now, causal inference strategies. So these are the approaches for establishing the causal relationship from observed and experimental data. So what you are doing is randomized control trials first. Gold standard. You do the assignments for the treatment, eliminates confounding by balancing the observed and unobserved various variables across groups. So that's how you define your randomized control trial, and this is your fixed control trial that you will use. Then the instrumental variables, use the variable that affect the outcome only through its effect on the treatment. Helpful when the randomization is impossible or treatment assignment is imperfect, then you can use the instrumental variables. Last is the regression adjustment, in which you statistically control for the measured confounding variables. Confounding variable can be anything, we have discussed about it. Age was one of the confounding variable. You measure statistically, you measure those controls, and you use those control to just the effect that you are seeing. So effect estimate is conditionally unbiased if all confounded are measured and correctly specified. If you have identified that age is one of the confounder in predicting the heart disease on the coffee consumption, if you measured it in the data, if you used it to correct it the data, then the the assumptions you are making, the corrections you are making are might be highly accurate as compared to the others. Then you go for the casual, sorry, matching methods. Matching method is a pairs of the similar unit that differ only in treatment status. So propensity score matching compare units with similar probability of treatment based on the covariates. So you consider all covariates separately and try to identify the matching comparison units to get the similar kind of probabilities. So considering the matching methods, not using the random methods for without considering the covariates, without considering the co-founders covariates. Then causal graphical models, DAGs. This visualize the causal relationship, identifying the minimum sufficient adjustment sets, help determine which variable to control for, which to leave out. So these are the 4 or 5 different type of methods to do the causal interference strategies. Either go for random control trials or instrumental variables, regression adjustment, matching methods, or causal graphical models. We generally use the regression type of adjustment methods, but it depends on the data, it depends on the question. The ultimate purpose is you need to identify the causal interferences, you need to identify the correlations you are seeing, the associations you are seeing, the relationship you are seeing is not affected by the confounders, by the different kind of covariates. No single method is universally best. Choice depend on the availability, data availability, background knowledge, possibility of assumptions, and the data sets, and the kind of data that you are using, from the distributions, from the hypothesis, and the kind of interpretations you are going to make. Example of the admission bias, we can take the example. So let's say overall, observe overall admission rate for the men, the applicants this, the admitted is this. So admission rate is 44%. For women, the admission rate is 35%. So initial conclusion is the data just 9% of the bias against the women, because males are have a higher admission rate as compared to the women. When you will analyze this data by department or anything, you need to consider this biasness. So when you are doing department A, B, C or something, men admitted, men percentage, women admitted, women percentage, women rate you are computing here, that should be men rate, women admitted, and women rate you have. So you are department wise level shows that women has a had higher admission rate nearly in all departments. So you need to see if in some department women have a higher rate, overall women have a lower rate, then there will be some departments which are highly biased against the gender, so specific gender. So you need to identify those kind of covariates, confounding variable, and then you need to define your object or your method, how to correct it. Identify the confounding factor. The paradox is explained by the following pattern: women applied more frequently to the competitive departments with lower overall admission rates, men applied more frequently to less competitive departments with higher overall admission rate. These kind of analysis you will make, these kind of conclusions you will make to identify exactly the co-founding factor. What are the factors those are there, what is the reason behind the higher admission rate of the women in certain departments, higher admission of the men's in certain departments, and then you will come up with the conclusions with your data. So if you'll come like this, then you will can rely on more on your associations, more on your correlations, and it might reflect the the true associations between two variables. When to stratified versus full, when you will analyze your data separately, men versus women for instance, or different age groups, or when you will combine those data groups, it's very very important. And you can answer this question like, stratify and confounder affect both treatment and outcome. If that is a confounding factor and it is affecting both, you should definitely stratify and analyze your data separately. If it is a heterogeneous effect across subgroups, if you're seeing the completely different effect in the males, completely different effect in the females, you definitely need to stratify and analyze it separately. Direction of effect differs between the strata, then you need to stratify and analyze separately. Investigating the potential Simpson paradox, if you identified the specific potential Simpson's paradox that we discussed for the male and female data, then you need to stratify. When you need to pool, when you have groups that are balanced, no selection bias, when you have a homogeneous effect across groups, you can combine them. When insufficient sample size in the subgroups, you can combine them, or you need for overall population estimate, then you need to combine them. But when you are combining when there is a effect, covariates or confounding effect, but the effect is not that much, you can correct it and combine it again. So common causal steps, you should look for the lurking variables, unmeasured third factor that can create these spurious correlations, spurious associations, over control, adjusting for mediated that part in the causal pathway. So don't do the over controlling, otherwise it will also affect your associations. Colinder bias, conditioning on the common effect create the artificial association. If you are focusing on very common effect, it can create the artificial associations between any two variables, and which might be the spurious results, not the actual correlations. P hacking: if you are doing multiple testing without corrections, if you are trying all these statistical method just to get the significant results, just to get the p value less than 0.005, it might mislead your results, it might mislead your data. So here in total, the summary and key takeaway is: report the association with context and limitations, focus on the correlation strength, but it does not imply the causation strength. So focus on the correlation strength, provide the p values, confidence interval, all the information, and highlight that this is simple association, might not be the direct relation. Prefer randomized experiment designed whenever possible to establish the causal relationship. DAG graph we discussed, directed cyclic graphs to identify the co-founders, and plan appropriate statistical adjustment in your test, whatever test you are doing, whether it's regression or correlation. Beware of the aggregation artifacts like Simpson paradox. Always check for both stratified and pooled results. Whenever you'll do, divide those groups, do the statistical test in both groups, combine those groups, do the statistical test, you will be able to see if there is a huge differences between the groups. You cannot combine it, because if you'll do the correction, it will be overcorrected, it might lead to these spurious results. So you need to decide based on the data. So when faced a strong correlation between value a and b, what would be your first step before suggesting the causal relationship? Look for the potential confounding variables that could influence both A and B, creating the appearance of the direct correlation. If there is no confounding variable, you can report that this can be obvious relationship between A and B. If there is a confounding variable, remove the confounding variable from the analysis, see the relation again. If the relation exists, that means there might be a strong association between A and B. So those kind of exercise you can do before reporting your correlation results, and it will help you to identify what is correlation and what is causation. I hope this is clear in this module. See you in the next module, in which we will discuss about the regression.